This is the 7.2a, check your understanding, sampling distributions of sample proportions, pHATs. Suppose that 75% of young adult internet users ages 18 to 29 watch online videos. A polling organization contacts a simple random sample of 1,000 young adult internet users and calculates the proportion, a pHAT, in the sample who watch online videos. Identify the mean of the sampling distribution of pHAT. So when you think about the sampling distribution of pHAT, think about that's every possible sample of 1,000 young adult internet users from the population. So something we can't physically do, but we can think theoretically. And we have that formula for the mean that it will just be that value p, that 0.75. On average, whatever we take a sample of 1,000, we would expect a proportion of 0.75 to be watching online videos. Notice the notation there, it's mu sub p hat, the mean of your sample proportions. Calculate and interpret the standard deviation of the sampling distribution of p-hats. We're going to use that formula and check that the 10% condition is met. So is our sample, that 1,000, less than 10% of the population? Now, they don't tell us the size of the population, but they say young adult internet users. So we can assume that that is sufficiently large. So you can calculate the standard deviation, so sigma sub p hat. So that's the square root of p times 1 minus p divided by n, all under that radical, so 0.014. The proportion of young adults who watch online videos in a sample of 1,000 typically varies by 0.014 from the proportion of 0.75. So there's your interpretation of the standard deviation. Now, you really can't use this formula unless the 10% condition is met. So for checking that the 10% condition is met, you would write something like 1,000 is less than 10% of the population of young adult internet users. Is the sampling distribution of pHAT approximately normal? So they told us that in order to decide this, we would check the large counts condition. Do we expect at least 10 successes and 10 failures? So yes, because we expect in a sample of 1,000, 750 to watch online videos and 250 to not. And these numbers are both bigger than 10, so we're good to go. So the large counts condition is passed, it's met, so this distribution will be approximately normal. Remember, that connects back to a binomial random variable. If you expect at least 10 successes and 10 failures, will be approximately normal, and that's the same here. Find the probability that the random sample of 1,000 young adults will give a result within 2 percentage points of the true value. So your true value is 0.75. So it's like, what's the probability that you take a sample of 1,000 and you get a proportion within 0.73 to 0.77, right? Within. So it could go in either direction. And you want to think about how what you're testing, like what your observation, it's a proportion, a sample proportion. So we're doing this on the distribution of p-hats. So that's what this normal curve is, with the mean of 0.75 and a standard deviation of 0.014. When you're finding a z-score here, right, you're doing the observation, which is a sample proportion, that 0.73, that 0.77, subtract the mean, which is p, 0.75, divide by the standard deviation. And you get those z-scores. Find the area between them, and it's 0.8472. So the probability that in a random sample of 1,000 adults that we get a result within 2 percentage points of 0.75 is 0.8472. If the sample size were 9,000 rather than 1,000, so we're increasing the sample size by 9 times, how would this change the sampling distribution of p-hat? So as we learned in the past, when you increase the sample size, you're going to decrease the variability. Because now, in order to create every single one of these, like think about the dots, that like a big pile of p-hats, like we thought of this as a dot plot. Instead of each dot coming from a proportion from 1,000, it's coming from a proportion of 9,000. So the more people in your sample, the closer your proportion is going to be to 0.75. You're your variability is just going to decrease when you increase your sample size. Now, you could look at that theoretically and calculate the standard deviation and see that your standard deviation is going to be smaller. See how that denominator is bigger? Specifically by a third, or like 3 times as big. Your denominator is 3 times as big, so your standard deviation is a third of what it once was. So, I mean, here's a sentence. The shape would remain the same. It's still approximately normal. Shape's the same. The center would stay the same, still that 0.75, but the variability would decrease by a factor of 1/3. And hopefully I displayed that algebra here, why it's a third. If you take this number and you multiply by a third, you get this number. So just remember the sentence: increase sample size, decrease variability.